In the last few videos where we've been looking at analysis of variance models, the categorical treatment variable is what is known as a fixed effect because the groups in the study are predefined and they're of direct interest. Sometimes we have studies that are set up with what are called random effects. So this is where the groups are randomly sampled from a population of possible groups. So to illustrate, we have this data set here on walking stick insects, and let's just take a look at the data. So we've got 25 walking sticks, and the researchers measured the femur length by taking photographs of the walking sticks and then using those to measure the lengths of the femur, or I guess one of the femurs. And this study was set up so that for each walking stick, this measurement was done twice. And the idea here is that the researchers know that taking a measurement off of a photograph, there's going to be some measurement error there. And so the thinking is that if we do this, if we repeat this, and then we could maybe take an average of the two measurements to do an analysis. And so what we want to do here is we want to get a handle on how variable the measurements are for the individual walking sticks. So what that variability is relative to the variability of the femur lengths between the insects themselves. And so we're going to do that using analysis of variance with randomly chosen groups and a random effect. So let's take a look at the data first. So it's a little bit involved using code to set up the plot that we're going to eventually create here. So there's a few steps here, and then it's easier to just do the steps and show you the results than to try and explain all the ins and outs of the code, because it is a little bit complicated. So bear with me. So first of all, if we use this mutate function, then what this does is it sets up so this mutate function, I think it's in this library here, the dplyr library or package. And let's get back to where we were. So now we've got a new data frame essentially, where we've got the individual walking sticks. So for example, walking stick number 1, this column here is the femur lengths. So 0.26 was the first measurement, 0.26 was the second measurement. The average of those is 0.26. So that one's not very interesting, but let's take the second walking stick. The first measurement was 0.23, the second one was 0.19. The average of those two numbers is 0.21. So the average for the walking stick number 2 is 0.21. Walking stick number 3, 0.25 for the first measurement, 0.23 for the second measurement, and 0.24 for the average. So that's what we did by using this mutate function. And then we're going to create a graph so we can see the progression of the insects, the two measurements, and it's more revealing if we order the walking sticks from the shortest average to the longest average. So that's what we're going to do here using the arrange function. And then we need to create a new variable to keep track of the ordered specimens. So we do that like this. And then finally we can put all those pieces together in this quite revealing plot. So we've got femur length on the vertical axis, and then we've got the new order of the walking sticks along the horizontal axis, and the two measurements for each. So these are the two measurements for the I guess the smallest walking stick with a femur length, it looks like 0.14 for the first measurement, 0.15 for the second one, and then the next shortest one was 0.15 for the first measurement, 0.16 for the second measurement, and then so on all the way up to the largest walking stick on average, and it had a first measurement that was, what is that, 0.31, I'm guessing, if I track that along onto the axis, and then what was its other measurement? 0.27, I would guess. Okay, so that's the data, and then this is going to be our random effects analysis of variance model, and we fit it using LME, which stands for linear mixed effects, and it's in the NLME package, so you have to load that first before you can run this function. So let's do that, and the syntax here is kind of complicated, so let me go through it. So we have two arguments, a fixed argument and a random argument. So the fixed argument has a tilde in it, so we're setting up a formula, and on the left side of the tilde goes the response variable, which is femur length in this case. And then on the right side of the formula goes any predictor variables we have that are fixed effects. And in this particular example, we don't have any fixed effects for the predictors. So instead of just leaving this blank, we specify a 1 which stands for an intercept term. So we've got the response variable here, and because we have no fixed effect predictor variables, we just fit the intercept term for the fixed effects. So that's the fixed effects, and then the random effects. You don't put anything on the left side of the tilde for the random effects, and on the right side of the tilde we're going to fit a separate random intercept for each walking stick specimen for this particular example. And the way that we code that is to write 1 for the intercept, and then this vertical bar stands for given, and then this is the grouping variable specimen. This was the variable that kept track of each walking stick. Okay, so a little bit complicated, but there we have it. So this is the form of a random effects analysis of variance model for this type of design, which is known as a repeated measures design. So for each individual that we're measuring, we've measured it repeated times, twice in this case. But you could imagine other studies where the specimens might have been measured 3 or 4 or 5 times. Okay, so let's fit that, and then we can just take a look at what the output is for that model. There's a lot of information here that I'm not going to dwell on, but I am going to dwell on these two numbers here. So under random effects, we've got standard deviations for the intercept and for the residual. And if we were to square the standard deviation for the intercept, that would give us the variance among the groups. So in this case, the variance among or between the walking sticks. Okay, so we could think of, if we refer to this graph here, we could think of the variability kind of between the insects, in the sense that we've got some very, very large insects and some very, very small insects, and so there's quite a bit of variability there in their average femur lengths. So that's what the variance among groups is measuring. Whereas if we square the standard deviation for the residuals, then we get the variance within the groups. So if we refer to this graph here, and if we think about the variability of each walking stick, kind of how variable the two measurements are for each individual walking stick. So the variability for this one is we can kind of see it, visualize it in the graph by the distance between the 2 points. So we can do that for each of the walking sticks. There's a couple there that had the same measurement each time, so there's no variability for those two. But most of the others have some variability. There's a few more here that were the same measurement each time. Another one here. But if we think about the variability within each walking stick, that's what this quantity is. If we square this standard deviation for the residuals, we get the variance within the groups. So what we are focused on here is kind of the relative size of each of these two variances. So it's helpful here to think about a couple of extreme examples. Let's imagine that the variability within the groups was really small. Actually, let's imagine that it was 0. Okay, so when we come to draw this graph, it wouldn't look like this. All the points would be like these walking sticks, the ones where the measurement was the same each time. So there would be no variability within the groups. So in other words, there would be no measurement error. So that would be one extreme scenario, and that would be good in a sense from the researcher's point of view, because there would be no measurement error for them to worry about. They would know that each time they made a measurement, if they repeated that measurement on the same individual, they would get the same number each time. So that would be one extreme. Another possibility is if let's say if this number was very small relative to this number. So what would that mean? So that would mean that the variability among the groups or between the groups is being dominated by the variability within the groups. So we could imagine that this graph in that case would have really wide distances. So these lines would be large, but the variability from the very large walking sticks to the very small walking sticks, there wouldn't be much of a difference there. So this kind of graph in that kind of scenario would not have this kind of trend going from very small insects up to very large insects. That difference between small insects and large insects would be small. So this trend would be kind of flattened out, kind of more like that. But on the other hand, the variability of the measurements for within each individual walking stick would be very large. So these lines would be really big. So this kind of graph would be very large lines joining points that were quite widely spaced. But as we go along the plot from the small insects to the large insects, there's not much of an increase there. So that would be the case if the variance among the groups was relatively small and the variance within the groups was relatively large. So that's two possible extremes. So it sounds like what we want to do is come up with some kind of measurement that compares these two numbers in a way that we can assess the relative size of the variance among the groups and the variance within the groups. And so something that does that is something called the repeatability, or also known as the intraclass correlation. So to calculate that, we're actually going to calculate these numbers, but we're going to calculate them using this function here, which is going to calculate something called the variance components. These two different variances are called the variance components. So if I use that function, and then let's just see what that gives us. So here's the variance among the groups. That was this number here. And then here's the variance within the groups. That was this number here. And there's another way of calculating the variance components, and this matches up more with what's in the textbook. But it's much easier to just use this function here. So I'm not going to go through this part here, which is kind of doing hand calculations to calculate the variance components. So instead, I'm going to pick out this number, and I'm going to call that var among, to stand for variance among the groups. So let's just confirm that. So there's the variance among the groups, and then I'll use this to calculate the variance within the groups. So we'll just confirm that value. And then if I take the variance among the groups and express that as a proportion of the total variance, so by adding the two variance components together, then what I'm going to get is the proportion of the total variance that is present among the groups. If I calculate this ratio here, so let me do that, and that's what's known as the repeatability. So in this case, it's 0.75. So we could express that as a percentage, and we could say that an estimated 75% of the total variance in femur length measurements in the population is the result of differences in true femur length between individual insects, and the remaining 25% is the result of measurement error. Okay, so just kind of think that sentence through for a second. We're expressing as a proportion of the total variance how much of the variance is between or among the individual insects. So just referring back to this graph again, it's how much of the total variance that's expressed in the plot as a whole can we attribute to actual true differences in mean femur length between the insects. So like from the large insects down to the very small insects, how much of the total variability is the variation between the insects. So 75% is that's what that represents, and then 25% is measurement error. And so this is useful information for the researcher to know. Ideally you want high repeatability, so that you have some reassurance that if you were to take repeated measurements on the same individual, that you would tend to get the same measurement each time, that there's not a lot of measurement error for you to worry about. So that's an example of a random effects model. In particular, it's a linear mixed effects model that we're using in the context of a repeated measures study. Later on in the course, we'll look at another type of random effects model that will come up in a slightly different context, but it'll use the LME function again.